Welcome to Evolute Migrate and AI-based containerization here at the Conf42 Cloud Native 2023. We're going to talk about how to automate any software from its source environment over to the destination in a matter of minutes. It's so very important as your CTO comes to you and asks you to move across cloud environments, or maybe you're a developer and you're responsible for a complex application or hundreds of applications, and you need to ensure that they reach their destination. With AI-based containerization, we're able to ensure that we get the most native artifact in the destination and be able to do that with razor-sharp precision. So we'll talk about how AI is able to achieve that capability and how we're able to ensure that whether you're trying to modernize, migrate, or transform that software, we can ensure that it is successful. So we'll go through an overview of Evolute Migrate. We'll also talk about the BCD framework and our software capabilities. We'll delve into a demo, and we'll finish off with a couple of scalability patterns to ensure that we really understand the rate at which we can take these artifacts and move them to their most production-oriented scalability pattern as we conclude for today. So in order to know where we're going, we must know where we've come from. And it's really interesting to see the developments that have been in this space, and it really does help to shape context for us. We're really excited that we were able to introduce the first containerization capability in 2016. Since the beginning, we really created the capability to move software into this artifact in a very native way. So we're super excited about the patents that show that. And what that really boils down to is that we were not only the first, but also one of the most comprehensive abilities today to be able to achieve this capability. We saw in about 2017 that Google was able to introduce the capability to also do containerization. And we've seen a couple of developments since then. We began developing our AI-based containerization around 2018. We also saw the purchase and acquisition of companies like Melistrata in the space. In 2018 as well. We've seen in about 2019 that companies like Docker created the MTE program. And this was really an amalgamation of a number of different consulting firms coming together and ensuring that enterprises were reaching their destinations. In 2020, we saw App2 Container being released, which was really focused on greenfield software, and Amazon has continued to launch these things and mature them. We've also seen around this time that we were able to launch our AI-based containerization capabilities and have really been working with a number of leading companies to get that to its highest peak. We've also seen Azure migrate around 2021, introduce its containerization capabilities. And we've also seen open source projects that are able to really introduce their ability to evaluate core software and create images, such as the Conveyor project. And so many developments in space, and we're super excited. Again, we do believe that we've created one of the most comprehensive abilities. So we've been able to do graphical as well as obviously non-graphical software. And really what this means is that for the ecosystem, we're able to really accelerate the rate at which software can reach these cloud native formats. So let's get a little bit more into BCD. BCD is binary configuration data. And what this framework really says is that if we can look at a software artifact in its source environment and put any component into either binary, configuration, or data, what that means is that we can make that software artifact more portable across the cloud. In order to understand how this data-based or AI-based approach works, we really have to understand the premise of it. We'll reserve a little bit of this deeper dive for later on, but just let's talk about it at a high level. For our input coming into the software, we need to understand a breadcrumb. And if you're familiar with the iRobot analogy, if we ask the right question, then we will get to the right solution. And in this case, we just need a breadcrumb. We just need an input that gives us a reference to the software. So in this case, that input is either the application binary, a package, a file. really anything that references that unique piece of software. Now, obviously, we can provide you a list of the software that's running on that environment, but this allows us to ensure that we understand the input. Now, again, we're going to introduce how you can use BCD not only through the Evolute Migrate software, but in your own modernization or containerization capabilities. We believe that this removes a lot of the overhead when you're cognitively thinking about how do I take this software from point A to point B, while most will go into that software and try to understand all the intricacies. And if you have to do that over 100 applications that have been created over many years, this becomes very complex. And even if you're a new software developer or a new startup, moving your software into a cloud environment or cross-cloud environments, maybe into an on-premise environment, being able to ensure that software gets there successfully, you also need to understand how the enterprise's cloud environment works. And so really ensuring that you understand how to mobilize your software via BCD is also something that's very important as a part of this talk. And so again, we'll talk through how you can better containerize your software, just understanding this model. Going back to the input, execution, and output. So our input being, again, an application binary or file, and the execution, in this case, we'll be seeing Evolute Migrate as we move into our demo. But again, BCD, binary configuration data, really looking at how you can analyze your software and put it into these buckets and then allow that to move will really help you to automate your software capabilities. And the output is very clear. We can move into really any type of form factor. Obviously, we could do VM to VM. We can go from core code base into a container. In this case, we'll talk about being able to go from VM to container. And that really is the precedent for being able to go into serverless, Lambda, really all of these technologies that are new and cutting edge are based on the container technology. And so being able to do that in a Kubernetes environment, whether you're across a public cloud, such as Google Cloud, AWS, or Azure, is all based on your ability to leverage Evolute Migrate and or the BCD framework. So it really makes for an exciting execution once you get the hang of it. We can talk about this all day, but it's always exciting to really get into a demo just to see the software at work. Now, what you'll see is we're actually going to be running Evolute's Migrate. This is our command line for this is Chrysalis. Chrysalis is the stage where you move from a pupa to a butterfly in that evolution process. So that's our software's name. We actually are going to execute this, and we'll see that it will connect to the source environment. It will be able to pull that application, transform it, and create the containerized artifact. So again, we'll connect to our guest apps. We'll tell it to only give us the base artifact since we're going to run through this interactively, and we'll ensure that we're able to see the execution of it in real time. So let's dive in, and what we'll do is we'll start off with our target applications, and we'll just see our ability to execute with this. So we can see that input here is Glassfish, and here we're able to see that we are going to take a middleware application. We'll start to run our Chrysalis software, and we'll point to our destination guest apps, source guest apps. We'll specify our privileged user. We'll go ahead and specify how to access that environment. And in my environment, that's the local environment. So we'll go ahead and just use the root user and specific keys. We'll also specify our staging. We'll specify our target applications, and we'll go from here. So we can quickly see that we're getting connectivity. What's happening right now is it's connecting to the actual guest apps, and it's actually comparing the source and destination to see the deterministic path that must take place. We like to talk about OSI, which we'll talk about how we create those translation maps here soon. But you can see that it begins to evaluate everything about the software. It creates the beginning and the end, and it also starts to parse and be able to determine which piece of this software is binary configuration and data. The reason that's important is because that's going to allow us to create unique container artifacts and make that software custom as well as razor sharp. So there you have it. We have our container image, and now we're actually able to copy this. Let's go ahead and we'll do a Docker run. And we'll get into this environment. So here we can see that we're able to, we'll go over to the guest app system and see the actual Glassfish source. This is how it existed in the virtual machine. So we can just copy that. We'll actually look at, we know that we have a database, so we'll just go ahead, start our database. We also see that we have a domain. So this is the application service, and we'll kick that off. And that's successful. And so this application has Pet Clinic. This is a demonstration app that's running in the environment. So we can go ahead and query this on the container environment that we just created. And we can see that the software is running and functioning as it should. Pretty cool, right? So this is exciting, just this ability to quickly transform. We'll actually go a little bit deeper and let's look at the actual Docker file. And again, this foundation allows us to easily bring it into a Kubernetes environment, but we just wanted the actual base of this, and we can see that the software was able to really see the destination was in an Amazon Linux environment, as well as be able to determine its packages and dependencies and everything needed to be able to run this software. So very exciting, this ability to have a very lightweight container image and capable of achieving this type of containerization and distribution. So in order to really understand this, we really need to delve deeper into how were we able to achieve this and how is AI used in a way that can achieve this. And what we're going to do is delve deeper into BCD, binary configuration data, to understand how the algorithm worked to componentize, categorize, classify, and ensure that the containerization would be successful. So again, the first step that occurs is that we need to understand where our software begins and ends. So what that amounts to is really that we needed to create a cluster for that software and understand its interdependencies and intra-dependencies, if you may. What are those components that are running within the software? What are those components that are running outside of the software? And what are their relationships between them? We were able to do this classification, and once we had this particular understanding of the software, this allowed us to create the appropriate container image. And a 3-tier or multi-tier type of application, which we'll talk about, the actual BCD framework and Evolute Migrate would be able to understand those relationships. And so understanding the actual classification of the software is very important. We were able to do this via the effective technique of k-means clustering, creating a cluster of the application of what belonged inside of it and what belonged outside of it, and really use this type of machine learning to achieve that capability. Now that we understand the application and its inter and intra-dependencies, we are actually able to now create the container artifact. And so we leverage decision trees. We really start off at about 7 or 8 base paths, but through the number of different options, through operating system capabilities, through the actual frameworks, dependencies, the destinations, and the sources that we're coming from, there typically is about 3,100 paths that the software can take deterministically. So we can't run this software in a way that it's undeterministic. We have to ensure that the software will reach its destination per execution. And so, again, we were able to leverage the decision trees to ensure that it was able to reach that path. Now, there does come a point where something new comes up and we are able to get it into the destination as optimistically as possible. And we really haven't come across a scenario based on our understanding of the world as it exists in a way that we weren't able to create a deterministic output. So we're super excited that the 99th percentile of software has worked. We saved the 1% for what we may not have experienced yet, although we've implemented this in many different enterprises and many different capabilities. So we believe this will work in your environment as well. And so once again, getting that ability to see how BCD works and really starting to think about when you look at a software, are you looking at it in terms of all the intricacies and components, or are you looking at it in terms of what are the pieces of applications, what are the pieces of configuration, what are the pieces of unique data, and where do I need to bring those in order to be successful will help you to be able to achieve this at scale. As we move into our runtime, it becomes very important that we separate our build from our run because we need to be able to move to any specific destination. And we were able to do this. And in doing so, again, we can run in any cloud environment. We can come from any source environment. We've seen some exciting source environments and some very legacy ones as well. We'll talk about that. But the point being is that we can really do anything new or anything old. And so it gets exciting to really see this work across a very large majority of software. So this also allows us to understand those dependent relationships. And so if certain services need to start before, as well as what components need to be separate, we're able to achieve that in the destination runtime. To go a little bit further into that, again, that classification, configuration, and containerization, those steps in the software are very unique. And as we gather our input and really are able to understand the breadcrumb or artifact that we have, we really are able to classify that software. And again, our ability to provide a list of software as it exists is very straightforward because of this capability. And so you can really just go and select it as you leverage our more polished CLIs and UIs. That ability to, now that we have the understanding of the application, once again, we're able to really evaluate what software language is it using, what is actually the libraries and dependencies, what are the static and dynamic variables, where is the storage, is it local, is it remote, and where does it belong in the destination? And so you've seen a very simple use of the CLI, but there's a lot more configuration options that can be used to ensure that you reach your destination in a single execution. And sometimes we're using this iteratively so that we can understand the software ourselves. So this is great for dev and test and really understanding those intricacies very quickly in your environment. Other times, we're really just wanting to have a very fast modernization. And whether you're doing just migrating, moving over from one cloud to another, modernizing where you're actually using that container artifact to achieve new technical capabilities, or you're transforming, you're using the software to be able to reach new business capabilities, all of that is possible within this migration or modernization, or rather transformation. And the reason that is because once I transform, now if we can imagine, much like ChatGPT, where its inputs are able to, is typically text, and the output is typically text. It could also be code, right? Our input is software, but our output is software as well. So the ability to put a serverless API or other types of constructs around this software and achieve new experiences for customers is also possible. So again, this is why we need to understand the software at this level of intricacy, because performance also matters. Our ability to scale to zero also matters. And so understanding at this level of granularity gets the software functioning well. For your personal use of BCD and just understanding that framework, you may not have to be able to achieve everything the software achieves, but your ability to understand the software in a way that ensures that you know how to deterministically get the software over to the destination is a feat in of itself. And so once again, when we containerize, we're able to ensure that there's proper instantiation, proper ordering, clustering if need be. That could be the clustering of a 3-tier web app. That could be the pattern of a scale-out database, so on and so forth. So we'll talk more about that. But the point is that we need to understand those relationships so that we can achieve the scalability. So that you can continue to see how this framework is working, we want to delve deeper into the container manifest. And we're going to do that with an in-house developed software. This software, again, we try to bring up some edge cases. There's plenty of new use cases where we've taken, something that's been only out there for a couple of years, or maybe the software has been greenfield. Again, code to container is also very exciting capabilities that we've put out there. But the ability to really take software as it exists in its current environment, in this particular case, this software was created 20 years ago. And, every operating system vendor and everyone said it wasn't possible to be done. And we actually had done it a few weeks prior to those statements being made. And so it's exciting to see what you can achieve when you truly understand this, plus some of the computational truths that we'll go through as well. So with this example application, let's look at how when we take a software through this approach, how we're able to get it to its destination. And in this case, we'll look at the destination container artifact to see how actually it was able to be organized by leveraging BCD. So here we're leveraging the broker app, and we can see that binary and configuration allow us to evaluate the application. In this case, we're moving the data over to Azure SQL. And in that case, we're recognize that ahead of time and are able to ensure that the software executes across that requirement. Here we can see that the container manifest is able to account for the application-specific components as well as those that are purely configuration. This configuration and these pieces are unique to the instantiation of the software. For multiple environments, we may need to create separate configuration, and this capability is made possible through the BCD framework and Evolute Migrate. So again, here we're able to see that the configuration is able to be tailored based on that. And that might become variables passed through, queried, so on and so forth as we mature that software artifact. As we look at the data components of this, we can see that the customer-specific data will reside in Azure SQL. We can also see that in our configuration, we need to point to that data source, and that we're able to do that really on the fly as a part of the BCD framework and the configuration that's occurring there. And so really, when we understand how BCD works, we can start to see how not only does it create a very organized way to ensure that the software reaches its destination, but also creates very organized manifest and are able to make it easy to scale in a cloud or Kubernetes environment. A couple of deterministic architectures that we could achieve for our scalability patterns. So now that we have our software effectively migrated, the ability to take that into its destination architecture is important. And we really want that to be quite deterministic. Now, there's many ways to scale applications, and this doesn't limit the ability, but we'll talk about the use cases that really serve about the 80 to 90 percentile of software. When you really look at the separation of software, we will talk about the computational truths that make that possible. But what's also important is to understand that the delineation occurs typically via a number of patterns. That typically occurs by the application function, that may occur by resource demand, and that may occur by the component, such as a package. What we really see here is that ability to separate that application. Maybe for a shopping cart application, we may have to separate the component that is the actual product library. And so those may be separate components, whether they're in an application that was made in a macro way or it was separated in its own native services from the beginning. Understanding that relationship will ensure that when we scale specific instances or components, that we're scaling for that capability. When we look at the actual resource demand, we look at scalability based on its hardware demand. So that can be CPU, memory, disk, network, and really ensuring that we're able to leverage the right architecture pattern based on that. And last but not least, again, a package. So something as simple as Nginx, maybe it needs to be separated or scaled independently to achieve the level of demand coming to the actual end component. In the case of the application function, we can see that there might be a multiplicative relationship where, let's talk about if it's an app WebDB, we might scale the application web service more than we scale the database. In those relationships, we understand our scalability pattern. We can use deployments and services to really ensure that those reach the correct destination and architecture. When looking at the actual resource demand, we recognize that we may need to create another instance based on, or another 100 instances based on resource demand, but really we can depend on our infrastructure components to do that. And so we might leverage a pod autoscaler to ensure that it's continuously meeting resource demand. When we look at the actual separation by component, again, this is just an N+1 pattern where the deployment count may be what's being changed to ensure that we reach our destination. And really this simplicity of component, this may also be the case in a scale-out database where you're trying to achieve quorum and you need to ensure that there's a minimum amount or odd number to ensure that you reach that. So again, no matter what the requirements of the topology, we can achieve this by understanding the scalability pattern and leveraging the framework to ensure that the end resulting manifest will achieve this capability. Now for a few computational truths. And what we recognize when we're really trying to do these modernizations, we've come across so many scenarios where someone has said, hey, this is impossible, it can't be done. Or there have been vendors, the vendor who created the software says it can't be done. Or even, companies have spent over 12 months trying to do it and said, look, this is just not possible. And in these cases, we kind of love these, obviously, but what's most important is when you come across these roadblocks is how you approach the problem. And what we see is that typically networking and security will be the biggest blocker. So you do have to understand, how to overcome those gaps. Typically, the easiest way to do that is by understanding how it works in a destination environment. Typically, and our Kubernetes architectures and our cloud native architectures are quite mature, so they are able to achieve every bit of security and communications scalability that any previous environment, but also by looking at it through OSI. Now, OSI basically states that any two disparate systems can communicate. When we look at OSI, we recognize, and some may know this as Physical Data Link Network Transport Session Presentation Application, or Please Do Not Throw Sausage Pizza Away, however you remember it. Just remember that whenever you're looking at software going from source to destination, to understand how is it achieved in the source and how is it achieved in the destination. Now, when we look at this, and this is actually how Migrate implements VCD, is it creates native translation maps across those layers. And so we know how something is supposed to behave in its source. We know how it's supposed to behave in a destination, and it's how we can achieve that scale. And so this, again, might be valuable for you as you reach that capability. The other big thing that we find informs how we leverage this framework to modernize is really in the relationships between components, and whether this is inter-relationships between networked components or networked applications, or intra. This might be IPC calls that are happening inside the software. We can understand those things in order to ensure that when they reach their destination, they're not only in a container artifact, but they're also able to meet the correct scalability pattern. And so when you're parsing your own configuration, it might be helpful to understand what are the relationships occurring in this software between softwares, and really focusing on that to understand the scalability patterns. And last but not least is understanding operating systems are abstractions. When we start to look at an operating system, we typically say, oh, it's impossible because of what's supported on this operating system. And it's very interesting to see that operating systems and our developers here have worked for many years to ensure that there is compatibility across kernels, and really the relationship between those packages and interfaces are there. And so understanding how a little bit about how those work is very valuable. And it really is why whenever you look at the actual attempts to modernize, you're able to achieve a lot of that across these capabilities. So OS and software modernization are key parts of digital transformation, and being able to achieve achieve that capability at scale is very important and very valuable. So again, the key piece here is when you're looking at the operating system, look at it less as this black box, which you can't change, and look at it more about like it's an interface and a set of packages and capabilities that must be complied to. And so typically in our regression testing, we're able to show that everything end to end will be successful. Last but not least, let's talk about some of the scalability patterns that exist for when we move our software into the destination artifact. So there's many different outcomes that we can achieve now that we understand the software so intricacy that we're mobilizing to its next generation platform or across cloud environments. We typically see this in the area of just enterprise digital transformation, where we might want to achieve software or OS modernization and really ensuring that we're getting to supported in latest versions are possible. As far as edge computing, when we look at things such as multi-axis edge compute and its requirements to understand latency, we start to understand how we can create distributed workloads. We start to understand how we can actually take the software, maybe we're for the data component or database component, we may be putting a read-only replica at the edge and allowing for write pass-throughs to occur. And so really ensuring that we're meeting the latency sensitive nature of the application is possible. Now, sometimes this means that the software may not be able to play as a cloud native application, but it can participate in a cloud native environment. And so again, these types of capabilities are very important to accelerating the rate at which we can leverage software in distributed environments such as the edge.